Hey guys, welcome to Pi&AI Bangalore, organized by DeepLearning.AI in association with Point Blank. I'm your host Aman. Furthermore, in today's session, we'll be discussing some of the best approaches to improve the performance of deep learning pipelines with a data-driven approach and easy to replicate TensorFlow examples to get best out of your hardware. So now I would like to welcome our speaker, Mr. Anirudh Koul. He is a noted AI expert, a UN TEDx speaker, and he's also one of the co-authors of O'Reilly's Practical Deep Learning book, and that's an amazing book and strongly recommend all the deep learners to please do read this book. And he's also a former scientist at Microsoft AI and Research, and he serves as an ML lead for NASA FDL. He helps scientists at Pinterest to incubate new technologies. Moreover, I would like to welcome all the participants who have joined us today for the session. So today we'll be exploring some methods to improve the efficiency of most deep learning pipelines, reduce wasted hardware cycles, and make them cost effective. And also we will covering how to identify and fix inefficiencies across different parts of the pipeline, including data preparation, reading and augmentation, training, and inference. Now, before heading toward this session, I'd like to play a small video message by Professor Andrew Ng and the DeepLearning.AI team.
Hello, deep learners. I'm Andrew Ng, founder of DeepLearning.AI, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, at DeepLearning.AI.
Sure. Hi, everyone. I make articles that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There's never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so let's you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pi&AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
The AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
Yep, and that's really important work. Well, it's nice chatting. And now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pi&AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in DeepLearning.AI, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot both from the talks and from each other. And once again, welcome to the DeepLearning.AI community.
Yeah, so basically Pi and AI Bangalore, it is a series of DeepLearning.AI meetups that brings together the global AI community. DeepLearning.AI is a AI-based e-learning platform founded by Professor Andrew Ng and Kian Ketan Forosh to make world-class AI education accessible to people worldwide so that we all can benefit from the AI-powered future. So, and this session is organized by DeepLearning.AI in association with Point Blank, a multidisciplinary community of students where everyone brings their own unique perspective. Students are encouraged to participate in various activities like open source contribution, competitive coding, and project development. You can check them out. The link is provided in the description. Now, without any further delay, I'd like Mr. Anirudh sir to please start with your session. And if anyone is having any queries or any doubts, you can post that in the chat box that will be answered after the session. Sir, over to you.
Hi.
Yeah. Hello, sir.
I was like thinking, how do I start this? I thought, I'll just bring the photograph of Dr. NG trying an app my team had
Okay.
built. Uh,
Okay.
so I'll keep that on the side. But this was an app for blind community. Uh, so I'll get started. So hi, everyone. Today's topic is basically about making things fast, getting them faster as quickly with as less work as possible, right? That's essentially what we all want to do, more bang for buck. So, and the way we have organized this is the 30 golden rules that if you remember them, if you note down and try to apply it to your programs, you might be running on Colab, but you can get like much faster power. And I'll share some stories on that. My name is Anirudh Koul, along with I used to previously work at Microsoft Research, and during the journey of deep learning since 2013, made a lot of mistakes. So I got into preaching how not to make the mistakes, and that eventually ended up as a book called the Practical Deep Learning Book from O'Reilly, along with my co-authors from NVIDIA, Siddha Ganju, and Square, Meher Kasem. And we basically saw the practical side of just like on deep learning or AI, you can understand the deep theory behind it. But if you had to apply it on an industry, what are like the way different companies like Google, Facebook, Microsoft are applying some of the things at scale? But for a beginner, how does one go from a beginner to a novice to somebody who could apply this at a startup to somebody applying it at scale? Whether it is training, whether it is inference, whether it is running it on cloud, mobile phones, robots, and I'll actually show you something I'm pretty proud of relatively quickly. So something I'm really proud of is the last page of the book says that if you have read everything till here, you might want to take your talent and apply on this Formula One style car called RoboRace. It's basically a driverless car, but it essentially runs on the same racetracks. So the challenge was that why can't you just, whatever you have learned, just apply it back onto a real car? Because last two chapters about autonomous driving. We just wrote it as a write-up, and people took that a little too seriously. And a few months later, this is the real car, which is driving AI on a couple of $1 million car at a racetrack. And this ended up on the podium built by some of the students. The students are still in university. Just watching that journey of them starting from the absolute basics to going on to the racetrack, that was pretty fantastic. So in a sense, if you're motivated by a project, take something that you get really excited about and start learning how to get to that step by step closer. Um, So let's start with our the number one evil in the life of any data scientist. It's basically waiting for your model to finish training. If you're in software engineering, you'll usually hear the word that you're waiting for your uh, code to compile. But for data scientists, it's basically waiting for it to train. And it takes a long time depending on the problems you're working on. And it's pretty personal to me because I have suffered through this for years, right? So I'll give you a very quick journey. So about 3 years back, I noticed something very interesting. What I noticed was that I was having to train a production for a production deadline. I had to train a particular model, and during the very same months, my weight was also going down by like 15 pounds, and that was very striking. Like, what's happening? Like, I'm not doing any exercise. I was not doing anything extra, but like the more I had to train, the more weight I would lose. Like, what's the correlation here? So the story was that my office had a walkway which would take about 2 minutes to walk. And so what I did is I took my program and tuned it so that it would give me the output of the every epoch every 2 minutes. And so I would turn it on, put my screen up, put it like in Zoom font, and then I would turn it on and walk on the walkway for 2 minutes. 2 minutes later, I would see if it has finished or not. No, I'll go and make another 2 minute walk. And so as I kept walking, I went from 8,000 steps to 15,000 steps in a matter of a few weeks. These are 15,000 steps every day. So essentially, the more I would wait, the less I would weigh. So maybe that's not the best way to, deep learning can have health benefits. I agree here. But we don't always want that. We want our programs to be faster. So I asked a friend of mine to give, any insights to you. So he sent a recorded message.
This is like common sense. The more GPUs you buy, the more money you save. That's right. The more GPUs you buy, the more money you save.
And that makes sense. You have more GPUs, your programs will train much faster, but maybe you don't have the cash. Maybe you're still in university. So that's where I think our particular lecture will go towards. Look, there is, just like in real life, there are things that you want, and then there are things you can actually afford. So my question to you is, could you have taken the car on the right and have raced it just like the car on the left? Basically sped that up, put some nitrogen oxide boosters into it, and get that out. And that's what we are going to do today. What we are going to do is take some bad ideas of normal code that you see on Keras tutorials, and then try to put some nitrous oxide boosters into it. Before I go there, I want to make sure that everybody knows the really basic part of when you go for training a deep learning program, and that usually happens with transfer learning. I think 95% of all AI training is a less number. I should probably increase it to like 99. For any real work that you would do, you start with a model that is already pre-trained on a problem. The whole idea is that if you have to learn a new instrument like melodica, this is going to take 3 months to start learning what the notes are and how to play that. But if you knew how to play a piano, then fine-tuning your skills onto a familiar instrument will be much faster, like 3 days. And that's what happens in deep learning. When you work on a problem, let's say you wanted to train Coke versus Pepsi classifier, for example, or you wanted to train a sentiment classifier, you're not going to begin from the problem from like just your data. What you'll do is you'll find a model which is trained on a much larger but similar data set, like ImageNet for images. And then what you do is you basically cut off the fully connected layers, add brand new layers there, and fine tune it for your problem. This is like the bread and butter of deep learning. If you have not trained this before, you could just follow these 30 lines of code in Colab notebook. It should just run on your mobile phone. But essentially, this is not more than 30 lines is what you want to know. And that's where our story starts. No matter which program you see, there are ways you can improve it. But before we get there, what is the underlying cause of your programs running slow? It is GPU starvation. So what happens is that when you train a program, your CPU is going to go and fetch that data from the hard disk. then it will decode it. If it's a JPG file, it will decode it so that it can load it into NumPy. Then it will do some augmentation, some rotation, some brightness changes and things like that. And then it will collect enough images in a batch of 64 or 128. And then it will send that data to your GPU. So all this time, the GPU was waiting there, peacefully, like with the patience of a monk, waiting, waiting, waiting. And now the GPU has the data, it will start attacking it for what you just paid, the thousands of dollars. And while it is attacking it, the CPU is idle. It's waiting for the GPU to finish the batch. And once the GPU finishes, it tells the CPU, hey, I'm free now. Start working on your stuff. The point is that when the CPU works, the GPU is idle. When the GPU works, the CPU is idle. That's a lot of wastage. We all learn about deadlocks and we learn in computer science problems like this. It's kind of like that, but it could have been solved with some very simple methods. So that's the number one reason if your program is running slow, and we want to make that fast. But by the way, if you can't measure how bad you are, you can't improve it. So we need to be able to measure that you are essentially a program is not as fast right now. So there are a couple of tools of the trade we'll find. The one that really helps people is TensorFlow Profiler inside TensorBoard. So TensorBoard is this sort of analytics level view of your deep learning programs, especially in TensorFlow. It gives you that analytical view. And one of the things you can turn on is this TensorFlow Profiler. In this image, I was training a particular program, and if you notice here, the CPU is occupied for up to like some 80 to 90 milliseconds totally, while the GPU was totally empty. And then the GPU kicks in, and I know that because it says the GPU and CPU here, but it's empty here, whereas when the GPU starts, the CPU is totally empty here, right? We are wasting resources here. So essentially, you could have the opportunity of improving it. And to turn this on, this is literally like one extra line you add. So this is a TensorBoard callback, which will turn TensorBoard on. And specifically, I'm turning on the TensorFlow Profiler, right? And like a normal callback that you might write in any deep learning program, you can just add that in here, and you will get this view for free. Easy. And then you can start digging in there. Now, that's one way of going about the problem, but maybe there could be an easier way to do that. So what we can do is go even simpler with something called NVIDIA SMI, NVIDIA System Management Interface, I believe. So what this does is that you go to command line or Colab and write NVIDIA-SMI, and it will give you a nice view of what's happening on your GPU. It will give you your electricity bill that you're going to get next month because of the program you just trained. It'll tell you the memory that it was occupying, hey, which program was running it. Obviously, this will be something Pythonic. But more importantly for us, it will tell us the GPU utilization. 51% GPU utilization means 49% was being wasted. And you don't want that. So that is where you see the opportunity for improvement. What you essentially want is this number to be as close as to like the highest number possible, 85, 90, that range, like 85% plus is what you want to aim for in your training. By the way, when you write this, it will tell at that particular millisecond what the GPU utilization was. So you might have to run this a couple of times to know, over time how it's working. So the quick tip you can do is you can write this thing watch -n.5 before any command. And what this will do is it will run this command every half a second and refresh it. So essentially what the benefit is, like, you don't have to manually do this yourself. It will just keep running on its own. If you run it in Colab, you could run this command NVIDIA SMI, but with like a exclamation mark, and it should just run that. So now that we know how to measure it, what you want to do is get this number as high as possible. So we are clear on that, right? So I was thinking like how to structure this stuff so that you could attack any particular piece of your pipeline. A good way we can do that is at different stages of your program. There's some parts we can improve while preparing the data, some parts while reading the data, some parts during augmentation, during training, and during inference. So let's attack the preparation side of things. So it's always good to start with bad ideas. So bad idea number one, having thousands of tiny files, let's say 10 kilobyte files. Bad idea number two, having one gigantic multi-GB file. These are called anti-patterns and you don't want them. Why? So what happens is that if you have thousands of tiny files, you would have to first go and seek the file, right, on your hard disk. And God forbid you have a magnetic hard disk still, which has, the needle has to go on the magnetic hard disk and seek to that particular file. That adds a lot of overhead. We are trying to reduce that overhead here. So bad idea. The other bad idea is to have one single big file, because if you have one gigantic big file, you cannot parallelize reading that entire file because it's like a whole big chunk, right? So that ability gets reduced. Worse, if you are using Google Cloud or Amazon S3 or Azure, where the files are actually on a network somewhere and it's one gigantic file. So your entire network is trying to download that one file in a single thread. If you had multiple files there, you could have at least attacked and downloaded multiple ones of them. So if these are bad ideas, what is the good idea? The good idea is you want to combine these thousands of tiny files into a handful of large files. And the sweet spot is about 100 MB. So what you want is, if you could combine these files, like these 10 KB, 10 KB, 10 KB files into 100 MB files, the speed would increase for whatever you're going to do down the line. And essentially save them as a TF record, and we'll see that in action soon. But TF records is your friend if you use TensorFlow. Second good idea. Actually, first the bad idea. So often when people read data sets, especially image data sets, you kind of see them doing the following. They have all the images on their hard disk. Then they will read it. And let's say this is like a photo taken with a nice Android phone or an iPhone, 4,000 into 3,000 pixel photographs. What they will do is they'll put a directory, read them in that resolution, then resize them into 256 into 256, right? And then they will train one epoch. Once they are done, they will iterate again. Read those big files, resize them down, train. And I think you can already smell the issue in here. You are spending the CPU cycles and resizing every time, which you didn't need to always. First time was more than enough, right? So what you could do instead is read the files once, resize and save it as a TF record. And next time, literally just read those, resized images for training. This makes, less wastage of reduction, less electricity bill. So that's a good idea. But good idea number three, you want to use TensorFlow datasets for many. So as any data scientist would say, the hardest part of like building and training things is not actually on the training part, it's actually on the time it takes to get to training. So when you hear about a new data set, especially a wild data set, you'll go there, get that data set, then try to understand the formatting of how the hell the researcher who published it had named it. Some people have these obnoxious names in the file that you then have to parse to understand this is the label. Sometimes it's in a weird directory structure. Sometimes a CSV file which says what this particular image is related to. And you have to do all that parsing around. And that takes time, from hours to days to get it to even read that particular format. Why would you do that if somebody has already pre-packaged that data set into something called TensorFlow datasets, where it can help you get a high-performance pipeline? So let's see this example. I'm going to show 5 lines, and essentially I think it's actually 2 lines when you see the real thing. So I imported TensorFlow datasets and said, hey, show me all the datasets. So everything from COCO to ImageNet to like natural language processing datasets are all available here, right? And so let's use CIFAR 100. And I made one call and I asked for the training split, but you could even do like training and test split into 33% in that single line. And then I went on my merry way for shuffling and batching. But again, I didn't have to download it. And if this is a big data set and my internet connection in the middle broke up, then I'd have to re-download it. I don't have to do anything in that because TensorFlow datasets is handling that behind the scenes. And this makes life really fast and easy. So good idea. By the way, here's a quick tip. If you want to get famous and your name to be cited by every researcher in the world, what you do is you publish your own TensorFlow dataset. because people will then download your TensorFlow dataset and start citing you in their papers and other things. So it's a great way to democratize things and become famous at the same time. How cool is that? So now that we know how to process the data, let's talk about where the money is really. It's in reading the data fast. And if you hear anything from me, and if you remember one thing that I'll say in my entire presentation today, it should be tf.data. TF.data is the gateway to high performance training pipelines. So what I'm going to do in the next few slides is I'm going to show a basic piece of TF.data, which is okay speed, and then we'll make it high performant. Okay. So we'll see the before and after in a few slides. So here's the before. So I basically am, in this example, listing all my files in the TF record in a particular folder, and I built a TF record data set. Okay. Uh, and then I basically built a data set. It did shuffling. Okay. It did repeating the data set because I'll be repeating through a couple of epochs. I called a particular example to parse that. It could be any function. I called a function to resize the image. It could be any function again. And I batched it into 64 size. Not rocket science, simple, clean. If you don't understand, I didn't understand the first time either, but I played with it and it started working, and I was happy till I realized it was slow. So then starts, how do we make this fast? So the first thing we'll attack is the first thing we mentioned in the slide. What is the cause of slowness? Is GPU starvation. GPU waits for the CPU to generate data, and CPU waits for the GPU to finish computation. We don't want that. How can we solve this? How about if the CPU, when it processes the data, it actually puts it in an intermediate buffer? And the CPU just stops talking to GPU. The relation is cut. It's a divorce. Instead, they both find their friendship with this buffer where the CPU keeps dumping the data. And now the CPU just has one job: read data, dump it, read data, dump it, read data, dump it. The GPU also doesn't wait for the CPU anymore. All it does is it keeps checking this buffer and removing the things from this buffer. And now its job is to take the items from the buffer for the batch size, train it. Then take the next batch size, train it, and keep removing it. So now we made there was a synchronous waiting cycle, and now we made this asynchronous because there's no waiting involved anyway. And that is the key thing. By doing that, and the word here you want to hear is being asynchronously pushing data into the buffer. It makes things fast. And to code it, it literally is one line, right? It is basically just writing the word prefetch, and you say the buffer size of how big the buffer you want. You as a scientist or a researcher or an ML engineer wants to tweak that buffer size, but that's literally one line change that you have to add there. And you'll suddenly notice, whoa, my program is already running 5 times faster, 10 times faster, just because of the magic that happens. So good idea number 723. I've forgotten how many good ideas we already mentioned, but it is to parallelize the CPU cores. I mean, even if you don't have GPUs, you probably have a lot of CPU cores on your machine. And why would you even, usually when you're using, chances are that you're not making, full use of parallelization. So all you do is, if you have a function, it could be any function here, you just add this extra keyword here called num parallel calls. And now what would happen is that it would parallelize it around. Now you have to set a number here. And what is a good number here? The good number would probably be the number of CPU cores. If you start adding 100 number here, I mean, it's not going to go faster anymore. It will, in fact, have more overhead of having to do more context switches. So just the number of CPU cores should be enough, but you can play with this number. All right. You're getting faster. Get even faster now by parallelizing the read. So you remember I said that, hey, one of the reasons you don't put files too big is so that you can actually read parallel files. So similarly, we can call interleave function, and this will read files parallelly. And this is really magical. So on your hard disk, if you have multiple files, why don't you read 4 files at a time, 16 files at a time? Similarly, you could do equal to the number of cores. More magically, if this data was on Amazon S3, GCP buckets, as your, uh, you could potentially be uh, parallelizing this, and that whole network call part now makes like life slightly faster if you're dependent on like a remote machine to get the data from. So it's getting faster. There are a couple of other tricks you can also apply. So often what happens is in deep learning training, I'll give a bad example actually. Uh, People have these files which are like one tiny file, one tiny file, one tiny file, one tiny file, one big file, and then one tiny, tiny, tiny file. So what happens is when you start reading, you read the first file quickly, second file quickly. So it's basically essentially doing first, third, second, third, fourth, and fifth. And at the fifth file, it gets stuck waiting to read the entire file and process it. And while it's stuck, the 6th, 7th, 8th, 9th thread are waiting, or like it's not processing any further. So this straggler thread, which was waiting, is causing the queue to basically slow down. It's kind of like a slow car which is like holding on the entire highway. You don't want that, right? So what you can essentially do, luckily in deep learning, we don't care about the order of things unless you are doing a time series problem. You really want to shuffle data in any case. So what you can turn is you can turn this deterministic ordering into a non-deterministic ordering. You say, I don't care for the order. So you can turn experimental options like this deterministic ordering to false. And now what will happen is when it starts reading the data, it will, if it comes across a straggler, I say like, keep doing what you're doing. I'm just going to go to the next things. And when you finish, come back in. So things become fast. So it's a good idea, whichever package you use, TensorFlow or PyTorch, there are some of these options available behind the scenes. And lovely. Oh, the best idea so far is caching it. In computer science, we all agree, whether you're using web browsers or anything, you want to cache data for something that will be frequently accessed. So if you're able to cache it, it will make things even faster because it doesn't have to go all the way to the hard disk and do all the work of reading it. So in this example, if your data set is small enough that it can fit in your RAM, just write the word cache, and suddenly you'll notice that after the first epoch finishes, the second epoch will just get fast really quickly. Now, if you have a much bigger data set, but you had a lot of pre-processing operations, you can then put this caching operation, but give it a file name. So some of the things like JPEG decoding and all that stuff, it will have like already cached after all that processing has happened, and it's a good thing. So there are other things you can do with experimental optimizations. I'm going to skip that for now, but there's a whole gold mine out there. Now, one thing that you might ask is, remember how here we set the number of parallel calls on the for I/O. We then set a number for the parallel calls for CPU processing, but you have to set that number 4 here. You have to set the number 4 here. You had to set the number of the buffer size. These are numbers you have to set and play with. Now, when you set them, this is for the particular machine you are running right now. Now, what happens if tomorrow your boss says, hey, I actually have a better cluster on the cloud, just rent a machine on the cloud and start running it. So you'd have to change the number. Now, imagine your buddy runs another program on the same CPU, not a deep learning program, some other process, and then suddenly that code is unavailable. So then you have to change that number again to get that best performance. That's a lot of work, right? And like setting that up takes a long time. How would you do that? Right? It's like this is looking a little messed up. Well, actually, you don't need to, because all you need to do is literally write this word auto-tune. So when you have any of these numbers, you set the word to auto-tune, and what's happening behind is just like you are trying to use AI to solve through a problem, TensorFlow is using something similar to an anthill, like an optimization problem, to find the best parameter to solve your size of whatever you are using, whether it's a buffer size or whether it's a number of parallel CPU calls you have to make. So what you'll notice is when you run this, the first epoch will be slow. The second epoch will be slightly faster. The third might actually get even slower. But by the time it reaches the 10th, the size of each epoch will start getting faster, faster, and faster. So it's a really good way to make things fast without having to, spend all night trying to play with the parameters. I like this. So let's look at the after. So let's look at this program. What did we do here? Same thing, reading TF records. We turned to certain options like the non-deterministic ordering. We did interleave to read these files and set it with auto-tune with number of parallel calls. We then ran whatever pre-processing function we had, like resizing or whatever, with, again, number of parallel calls. Now, this part is kind of common, reading and this, so we cached it. From now on, literally everything you'll read will literally be coming out of this part. It will actually ignore this. So you repeat that data, you shuffle it, you batch size, put a batch size here, and then you prefetch it. Prefetch, keep it like near the end. And this is fast. I like it. Most of the times, if you get this much done, bang for buck, your program is running fast, and you'll be hopefully having to wait much, much lesser. So that's good. Now comes to data augmentation. I actually should want to give a quick idea on after data augmentation, like how easy these things are. So one of the things in data augmentation is that we read the data, but when let's say you're working with a computer vision problem, you will take an image and you will have to you'll have to like rotate it a bit. You will have to change the brightness, the contrast, the hue. You might want to crop in things, right? So to do that, this usually happens, when you use a library like Pillow, when you use Keras. Keras has image data generator functions. Usually, most of this is happening on the CPU. Okay, and the CPU is running. And how many cores do you usually have? You have like 8 cores there, right? By the way, on your GPU, how many cores do you have? Somewhere about 2,000 to 5,000. So won't it be a better idea to parallelize it on the GPU instead of doing it on the CPU, right? Like you'll get like so much faster processing. And that's what you can do. So instead of using some of the, when you start with a tutorial, it's great and fun, but then when you go to the real side of things, you might want to change your augmentation functions from the basic Keras functions to tf.image. And this tf.image function will literally start using GPU augmentations. So you can adjust the hue. If you want to rotate it by 90 degrees, you want to do some cropping, this will all be done on the GPU and you will see things getting fast. One of the common things that happens is that by the time people get here, they are getting, they're usually getting fast enough, but the bottleneck now is the CPU. Like their GPU is like doing everything efficiently, but the CPU becomes the bottleneck. So that's the common reason for the bottleneck, that you are doing augmentations on the CPU. And now what you want to do is essentially get here and do that, do this. So here's the interesting part. When you try doing this, you could use the TensorFlow.image functions. Great. One problem that not every function is implemented there. Okay. There's another way of doing things. For example, you cannot rotate things by random degrees. Like you can rotate it by 90 degrees, but you can't just rotate it totally randomly. Okay. Now here's the cool part. You could put an augmentation as a layer in your network. So rotate my image by a total random degree is an available option in Keras inside your model. So you could define one of the model layers as a rotation function. You could define a model layer as a brightness function. So while it's training, because it's an entire model, the model is GPU accelerated, so it becomes fast. Okay, but while you are doing inference, when you are doing prediction, those layers don't turn on. So the good thing is that those layers are only being used during training. So that's one other option you have available if you don't want to use this tf.image pipeline, and it just makes things fast. I'll give you this really good example. So we have a program for students called Space ML, where people who are motivated by solving problems on planetary scale, climate change, they start learning AI to solve some of the problems. And we had students from high school who had no background. And 2 months later, 8 weeks later, they had made enough contributions and they got 6 research papers accepted. And many of those students were still new to AI, right? And they wrote those programs and they were training slowly. And then they started to apply some of these tricks. And they saw a 70x speed up in their training pipelines on the data part. And they got an 80x speed up when they also included the augmentations. So things which were taking 10 minutes were now taking about 6 to 7 seconds. So this is not rocket science is the point I'm trying to drive. This is like simple things. One time you play with it, you're like, how was I not using it before? So good idea to try it out. By the way, here's another trick you can use, and it comes from NVIDIA. So you know, so NVIDIA always wants to, make their name and build these solutions for industry, and they like to break benchmarks. So they have recently broken this benchmark of training entire ImageNet in under 80 seconds. That's a good number. How did they do that? So for that, they specifically built a fast GPU accelerated data reading pipeline. I'm not talking about training. I'm actually talking about the part about reading the data, loading it. So the thing that happens there is it loads the data, but when the image has to be decoded, it actually decodes it between the CPU and GPU. Now the data is on the GPU, so the resizing happens on GPU, the augmentation happens on the GPU, and the training happens on the GPU. But because the data is already on the GPU, it stays local, so it does not have to pass through between the memory and the bus anymore. It's like in the GPU itself. So things get accelerated really well. And this works both for PyTorch as well as for TensorFlow. So this is another good option that if you want to work on fast deep learning training pipelines but don't care about any detail, this might be one way of also going about using that called NVIDIA DALI. So check this out. All right. So the hope is that anything you saw till now is already making your pipeline smart and fast, and that's great. So the next topic that we'll come and attack is training. And this could be whatever, whether you're using PyTorch or TensorFlow. This is some generic techniques that you can do to make your things faster, but attacking on the training side. So the very first thing I will say is literally write that line on top of your program and just forget about any details and just see your program go hopefully 2 to 3 times faster. So this is called automatic mix precision. So the logic is as follows. When you train your neural networks, they're usually 32-bit. Well, these neural networks are usually pretty robust to noise. Why can't we train this with or like use 16 bits? Because if you use 16 bits instead of 32 bits, then you can fit double the amount of items in your GPU, in your memory bus, right? That sounds like a good idea. So when you run your program on a mobile phone, like on Core ML or TensorFlow and TensorFlow Lite, it actually does do that automatically behind the scenes. It takes your model and actually runs it with 16-bit. It's called 16-bit quantization. So why can't we do that while training also? Sounds like a good idea. Well, without going into details, it's going to be a messy item if you try to do that. It will have overflows and underflows if you try to do it yourself. So you want to leave it to the professionals who have built automatic mix precision inside PyTorch as well as inside TensorFlow. So what this does is it gives you the benefit of training at 16 bits while giving the precision of 32 bits and that stability that you get with 32 bits. So I can go a lot deeper into this, but I think this is good enough detail that you want to know and make life easy. One line makes things better. Number 2, tuning your batch size. Really helpful. So let's think about this for a second. So what I want you to know is this is the batch size. So I'm tuning the batch size and I'm trying to see how does it affect the time per epoch. And what I did is I ran this network MobileNet V2 on a 2080 Ti. I think it's about like 12 GB memory. And if you think about it, in 12 GB, a MobileNet V2, which is like a 15, let's make it a little easier. Let's take ResNet 50. ResNet 50 is usually about like 98 MB, so essentially 100 MB. How many ResNet 50 can you fit inside 12 GB? About 128, right? So before even working on a problem, my usual batch size will be that number closest to what I can fit in that GPU. So by default, if I know the GPU of my machine, I will, try to fit 128 things on a Resident 50 in a particular batch. So in this particular example, I started playing with, okay, I'm changing the number of epochs and see what happens. So let's play with this. If I set the batch size to 5, it was taking 100 seconds. I changed it to 10. It's taking like 60 seconds. That's a good speed up. If I started putting like about 100, it is gone down to 20 seconds per epoch. That's nice. I then started putting like about, I think this was like 700, 800, and it was taking 5 seconds. What's happening is that your GPU has the capacity to do things. And if you're not fully taking advantage of it by having a smaller batch size, it just has so much overhead that it could have done in that particular time. The time it will take to, I think the time it will take to run one batch of 5 images versus a one batch of 500 images is kind of going to be around the same, right? So that's where you could have had some benefit. And if you notice this is the line I got from NVIDIA SMI, which was the GPU utilization. And you can see that when I was using smaller batch size, I was literally wasting my, I think I should need to look at the red line and this side. I was basically getting like 20, 25% GPU utilization. But when I started to increase it, I started getting closer to that, 85, 90% territory. So long term, I will often get some plateau, but if you can get to 256 batch size, I think you are already in a good zone. So tune your batch size is the point. I should also say a negative thing, because I can't just keep telling one-sided things about making things fast. If you make your batch size a little too big, your training might convert slowly. Okay, smaller batch sizes actually act as a regularizer, whereas bigger batch sizes might take a longer time to converge, and sometimes then you have to use things like large optimizer. Just for reference, if you read some papers, recent papers from Google and NVIDIA, they're using 80,000 batch sizes on their clusters. So big batch sizes do happen, but you have to use special optimizers for that. So 256, good enough for most problems. Okay, another thing, use multiples of 8. Good idea. Bad idea, not using it. So what happens is NVIDIA was doing this experiment and they used a number for a batch size. They were happy. Then they used another batch size and they saw 5x speed up. They're like confused. Then they started using only even numbers and they saw some numbers actually giving lower speed throughput, and then other numbers giving higher throughput. And they noticed that as long as the numbers were multiples of 8, they were getting a good speed, like 4x. Actually, it's 4x to 5x speed up. What's happening? So what happened is as follows. Back in the days, we had CPUs. Then we got GPUs, which somehow also magically were helpful for training. And then started coming specialized machines or like accelerators for deep learning. Remember, GPUs were not built for deep learning. GPUs were built for graphics and video games. They just happened to be good for deep learning. But eventually, Google came out with TPU and NVIDIA came out with tensor cores. So on your GPU, it will have some tensor cores on top of your normal GPU, and TPU is just too specific. And they have some minimum requirement because their matrix multiplier is a specific size, right? So you want to make sure that you meet the minimum requirements of that multiplier. Otherwise, it will end up with a fallback accelerator, which is just the GPU, right? If you spend the money, you better get the value for it. So you want the number of channels in your convolutional layer filter to be divisible by 8. You want the number of neurons in the fully connected to be divisible by 8. The size of the mini batch divisible by 8. That's what you want to remember. My recommendation, use multiples of 64 if you're using NVIDIA hardware or 256. If you use Google TPUs, use multiples of 128. That's where you'll get the best performance. Good idea. Okay, select an optimal learning rate. This is the hyperparameter you tune, right? If you use PyTorch, Python lightning bolts, it has a best learning rate finder. If you use TensorFlow, Keras, there's a library I'm about to show called Keras LR finder. But the whole idea is that if you choose a learning rate which is too small, it will take a long time for gradient descent to come to the minima. That is your solution. If you use too high of a learning rate, it will just go, bouncing around without going to the local minimum, like the global minima. So you want a number which is just good enough that it will take the minimal number of steps to land here. And what we essentially are interested is the point of greatest decrease in loss. So you want that learning rate which leads to the greatest decrease in loss. So not the greatest loss, the greatest decrease in loss. It's kind of like uh, when you do differentiation, you go one step further to go to the greatest decrease in loss. And there are papers around it, but I'll just say use this library called Keras LR Finder. So here's an example. I had my model, I wrote my training script, but I added LR Finder, and I started plotting the loss. And this is showing me the loss curve. Okay. And now, in this particular example, it's plotting the change in loss. And I'm interested in the greatest change in loss, like decrease in loss. And that's the point. So for my particular program, this number will probably lead to the fastest convergence for my problem. That's the real takeaway here. So tuning your, if you want to keep it more simpler, just try it at 10 raised to power minus 4, 10 raised to power minus 3, 10 raised to power minus 2. Like try 10 of them and see, if one of them sticks. So that you can try. All right, something funky that I want to show. Here's a program. And this has one simple function here, convolutional layer. Okay. And what I did is I literally copied the same function below, but with one small change. I wrote the @tf dot function on top of it. All right. So literally the only change is above the function, nothing inside the function. And I ran it 10,000 times. What happened? This happened. It got a 10x speed up. Just by writing that one line, there's a 10x speed up. Okay, what's happening behind the scenes? That was a little puzzling. So what was happening behind the scenes was as follows. Back in the days when TensorFlow 1.0 come, it was running their training operations like what do I say? It was compiling the graph and then running it all in one go, kind of like how C++ programs run. I mean, yeah, it's built on C++. Okay, so that was good. It was fast. But for anybody trying to debug it, it was a nightmare. And PyTorch said, don't worry, just come over to me and we'll do that here in a very Pythonic way. So TensorFlow 2.0 came and said, okay, don't run there, we'll fix it for everyone. So in TensorFlow 2.0, the eager execution is like turned on by default. Essentially, when you write a line, it runs right away. Okay, good, really good for debugging. You make lesser mistakes, your program runs faster. I mean, your coding to get the program happens faster. The problem is that if you have something, there's a potential overhead for any function inside or like any model inside. And it's not as bad of a problem if you have like an entire RESTnet to run. Okay, that's fine. But if you have like these smaller, tinier things, which you have to do a couple of million to billion times, that becomes like a bunch of overhead. So this solution is that all you do is you write @tf dot function and it converts it from the eager mode to like the graph execution mode. Now you understand why this is running as a graph, like as a compiled graph, not exactly as like a line by line thing. And that's why it becomes faster. So that's like one quick thing you can do on top of your programs. Sounds fun. All right, here's another strategy that you can use. And I have found it really, for the longest time, I was trying to find if anybody else has done it. Is there a name for it? So eventually turns out it's called curriculum learning. But let's go with the simpler version, which is overtrain and then generalize. So the idea is follows. Imagine you had to learn French. Okay, and I tell you, okay, how are you going to learn French? So one solution is you pick this big bulky dictionary with 20,000 words, and you start reading it from the word number 1 to word number n and start learning it. Right? I'm pretty sure by the time you read the end, you don't even remember the second last page of it. It's just hard. Right? Nobody learns like that. Here's another way. What if I give you 50 most common words in French? Okay, and you learn those 50 common words in French and you get a little confident. But maybe you might get a little too confident because you just learned these 50 words and you think you know everything. So the moment you start getting overconfident, I'll show you 100 more other words. And you'll again get a little bit underconfident, like, oh shit, I don't know these words, I need to learn this. So you start learning this, and as you start going overconfident, we again show you more words. So essentially, you want to overtrain, and when you start overtraining, then you start generalizing. That's like a cool concept that you could have done. Sounds about right. So we can do this in many, many ways. And here are a couple of ways. So first example, progressive sampling. Imagine you wanted to train ImageNet. It has 1,000 classes. That's going to take a long, long time. Worst part, you don't want to train the whole thing to realize you made a mistake and this thing doesn't work after waiting all these days. So here's a good idea. What if you only train for 10 classes instead of 1,000? Once you start doing good on 10 classes, then you start showing it maybe 20 classes. Once it does good on 20, maybe then you show 100. Once it does good on 100, then you show 1,000. And so if you had made a mistake, you'll know that early on, but it can gradually generalize, and you can get something working more faster and learn your mistakes early on. So that's a good idea. Another idea is progressive augmentation. So imagine you have the data set. What if you don't do any augmentation and just train it as it is? So it starts to learn from the current image patterns with no augmentation, and it will probably quite possibly even memorize the data set if your model is like good enough. But that's the thing. The moment it starts to overtrain, then you start turning its augmentations on. So you start with 0-degree rotation, and then you go like 20-degree rotation. Have no brightness, and then start getting like plus minus 10% in brightness. So start going harder on your model once it has at least done something to learn from the basic patterns. Another idea which was popularized by Jeremy Howard from Fast.ai is progressive resizing. So think about it. If you had an image which is 256 into 256, if I reduce the height by half and width by half, then half height, half width essentially is 1/4 the area of the image. That means I can fit 4x the items in my batch size. So I can get 4x the speed up. That sounds cool. So what if I actually reduced my dimensions by 1/4? So I pick a 64 height and 64 width image, and I train with that. I can get a 16x speed up. So what if I take data which was 1/4 height, 1/4 width, 64 into 64, and train with that, and get something trained really quickly? And that will be cool, because if I do that, I have something trained fast. Then I start fine tuning it on 128 into 128. Once it gets better, then I start fine tuning it on 256 into 256. The idea is progressive resizing. And what's happening is that at smaller resolutions, you force it to learn higher level details, broad shapes, broad colors, right? And then when you give it the higher resolutions, then it starts to learn the fine grained details. And that's actually pretty valuable. So essentially, you want to do progressively, and it will save you a ton of time and energy in whatever you are doing. So this is where you take the tutorials that you get pre-built, and you start applying, learnings and playing with it to see how the world works. All right. There's a high chance that you might not actually even have installed a good version of TensorFlow on your particular machine. Bad idea, right? So essentially, when TensorFlow was built, it's built literally for every kind of hardware, from the fastest TPUs all the way to a Raspberry Pi, right? So it supports some instruction sets, but it's built for like literally every case. And you might have a very specific instruction set on your machine. So you might want to install that particular version, right? So here's an example. One way is that you could have like compiled TensorFlow based on your instruction set, and they are like easy ways to find which instruction set. So this would potentially have been the fastest install. Maybe that's a little too much, right? To go and build TensorFlow all the way from scratch. Couple of other things you can do is you could just go to Anaconda and download their TensorFlow version, because quite possibly if you have an Intel CPU like a Xeon CPU, it can give you 2x speed up in inference, because internally it figures out which instruction set of TensorFlow to use and install for your machine. So that makes life really, really easy. There are other ways you can make things fun. If you know the number of CPUs you have, you can set at the top of your deep learning program the inter-operation parallelism. So it defines the number of threads that you want to turn on based on the number of CPU threads. But within one CPU, you can have multiple cores, like 2 cores. So that is called intra parallelism. And you can also set the number here. And funny thing is, all these details are literally available in one line. Like you write LSCPU and you can just see that thing here. Like this is not some convoluted detail that you might want. Now the hope is the designers of any deep learning platform should just have these things running behind the scenes. But as times have shown, sometimes they haven't optimized it. So you could do this and get all the control for your machines. All right. Obviously, if you've done all this, I think you're as fast as potentially possible to running it. So then you go to your boss or to the head of your department and say, you need to make this fast. You need to buy me this NVIDIA DGX2. It costs $400,000. And it's 2 petaflops with 16 GPUs, and it consumes the power of 7 air conditioners. So I probably won't install it in my home, but definitely in a better place. So that's something that you could have gone for, right? Or if you had more money, you could have gone for this NVIDIA 800 chip, literally a single chip. Let me repeat, a single chip here, 5 petaflops, and the starting system is at $200,000. Let me put in reference. This had 16 GPUs, and this has 2 petaflops, and this is one chip with 5 petaflops. So maybe you can build a system with 10 of these, and your systems will be fast. Because I think if you have reached till like the 2 slides before, you probably deserve this because your system is as fast as possible. If you want to be even faster, so I went back to my friend to get a little bit of advice for you at Pi.AI, and here's what he said.
Work with me here. The more you buy, the more you save. That's right, work with me here. The more you buy, the more you save. This is not a complicated talk.
We understand his reasons. So what we could do is now start going in the direction of parallelizing it on multiple machines, distributing it. You could rent out machines for cheap, right, on any of the cloud providers, and scale your program horizontally in 2 lines of code. So essentially, whether it's PyTorch, whether it's TensorFlow, there are ways of distributing it, and you don't have to write too much, right? All you need to make sure is that you have multiple GPUs attached to your VM, and this works nicely. You could both have ways of using it for 2 or more GPUs on a single node, or you have multiple nodes, like easy ways to do that. There's also another program called Harvard from Uber, where you could, how you write Python, TensorFlow, and like Python, and then the name of your program .py. You could essentially do your program.py here and essentially say beforehand Harvard, run it on 16 machines, and give the details here. So that's another way of doing that. So many ways out there. Now, something fun. Here's you're trying to do all this, but there might be a way that you want to see how the best in the world have done it. Like, can we learn from the absolute best in the world? And you can do that. So there's Stanford Dawn benchmark, where they have listed different hardwares on the cloud that you can rent today, and how this person, Mr. Chuan Lee, used this cloud to only spend $19 to train ImageNet. So in $19, this person was able to train entire ImageNet. That's impressive, right? But you know what's more impressive is that the entire source code is written here. So you just click on it and run and copy it, and you can get same amount of scalability and speed, right? So the best in the world, right? This is from March 2020. This is like $7.43. So I think this doesn't have a source code, but if you wanted to do it on Google Cloud, I think this might be a good example of using TPUs. So it's not expensive is the point I'm trying to get at. Another is how fast can you train? So again, on Dawn benchmark, there have been competitions, and I think it's 2 minutes 38 seconds spent with 16 machines. So that's also possible. So it's fast and cheap is the point I think you want to get. Uh, so that all the bonus that your boss has will be given to you instead of spending it on cloud machines. Now, if you want to see how hardware companies are doing it, there's an industrial benchmark called MLPerf. And MLPerf is more geared for hardware makers to let them fight. So, for example, Google here is trying to fight with NVIDIA and say, hey, if you train with our TPUs, you can train it in 1 minute. And I think this is, I want to say like 75 seconds, 80 seconds. There's like literally matter of seconds between this and this. It's 1 minute and some seconds. Okay, sure. Behind the scenes, Google was using 102 for TPUs and NVIDIA was using 1500 GPUs. So that's kind of expensive, but this just shows you, how much you can get to. But I'll ask you that why couldn't you just use, 16 machines from here to get it in 2 minutes, 38 seconds? Like the world is not running around. You don't need to be 1 minute. So that's a good thing, you can apply. Uh, Even in the worst case, with one NVIDIA Pascal GPU, you could have trained it in about 3 hours. So that's not bad. So it's all doable. By the way, if you want to get even faster, here's a quick tip. Rent Microsoft's supercomputer, which consists of 10,000 GPUs and 3 lakh CPUs. So OpenAI used this to train GPT-3. And that's how you're getting all those bonkers good results in the industry. So in a sense, if you don't have money, first make your program always really fast and then go for scaling it up, because you don't want to burn money by getting more machines before you even have the essentially fast machine running. So hopefully during today's session, you could see that many of these things can be done in like 1 line, 2 line. It's not as hard. And if you follow some of these strategies, it just makes life easy for everyone and gets you the result fast. You might have slides questions like, hey, where do I get the slides? So all you do is you email practicaldlbook@gmail.com and you should get an automatic reply back with these slides. So all you just put the subject line as wget pi presentation. And I actually had a gift for you for today. And this is the world where people don't prepare. So the gift is essentially all the things that you saw in the slides is actually an A4 size printout that you can print on your desk. So I usually have it printed out. So when I'm training a deep learning program, it's a checklist that I just tick mark, tick mark, tick mark if I have applied it on my program, so I don't miss out anything. And so you can just get that for free, that you can start applying and use it. So thanks for reaching out. I should mention that many of these tips are written in many more details on the book. So, check that out. And that's all I had for today.
Yeah. Thank you so much, sir. That was really an informative session. So now, we'll look, there are some questions in the chat box. So here our first question is that can integrated CPU plus TPU, that is Apple M1 Silicon, help in reducing GPU starvation problem?
Great question. For the M1, it seems to be the case in certain ways. So just FYI, if you buy a MacBook, it's not exactly the best machine for doing deep learning on the machine itself. You usually log into another Linux machine with a GPU usually. But in the recent experiments, they saw a 7x speed up by using the M1 with TensorFlow, which was optimized for that. And it's a great question because exactly that's what they were able to prove, that being integrated does help in speeding up things. So great question, and you're right.
So sir, another question is that how to build custom data generators as efficient TensorFlow dataset?
I believe that if you use the TensorFlow data pipelines, as long as you can get things in TensorFlow record format, from there it should be buildable. I mean, there are tutorials out there, but if essentially a particular data set I was working on had a lot of customized needs. So what we did is we packaged it as a TF record where the label for like what the label for this particular thing is, and all the metadata was already written there. And it was literally like a function call where we were returning the image and the label as part of the function for the deep learning program to train. And before we started, we thought this will be very convoluted and this will take a long time. Turns out it's literally a function return call where you pass the image and the label back. Like in Python, you have like two things you return from a function. It worked out really nicely, and we got a 70x speed up.
So like our next question is like how to start open source contribution in machine learning.
Oh, beautiful question. Uh, Look, usually what happens is if you're going for a job, let's say, there are two problems to solve. One problem is uh, do you to pass through the interview if you get interviewed, right? So that means that you have the skills and you have built things, you have learned things, and you can pass the interview. The second bigger problem to solve is why will you get called in the interview when there are 100 other candidates trying to get for the same position, right? And that's where the beauty comes as showcase projects. You want to put projects on your GitHub in open source that you built. Some projects will be like personal learning projects. Other projects will be where you are contributing to other source codes. So they are good guides. If you search on YouTube for how to get started in open source, Facebook Developer Relations has these, generic videos on how to get started to give you some confidence. Learn GitHub, and then start attacking a particular. I mean, once you have built some of your own projects, so you have like the necessary skills, you have learned good coding conventions like PEP 8, use a linter, comment. I mean, we keep saying comment, 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 but unless you use a linter, unless you like have to push your code to your own GitHub profile, you don't learn that. Try to see how to, this is something called read the docs package to build a documentation for the package that you are building. And once you've done that and built a little bit of familiarity with GitHub, which somehow colleges they don't usually sort of teach about that. So once you're done, then start attacking. Can you, contribute to an open source project where you can contribute and your work gets used? So always focus on the impact. If you write code, nobody cares. But if your code is good enough that it adds value to somebody else's life, that it's used as a pip package, that adds value. I might say, if I should probably give a plugin. I run a group for citizen scientists, where if NASA or SETI Institute has a particular problem of public interest, like in climate change. So we get a group of volunteers together to contribute in open source. So we call it open source research, where it has parts of AI, machine learning, and then research is great, but unless somebody can use it, it's just useless. So we are building a search system on 35 petabytes of unlabeled data. And when we started, we got like a group of high schoolers who ended up all with the research paper. And now we are polishing the code and putting it in open source and getting it out. So, if you want to, work on this, it's called Space ML. Just reach out on that same email address. And it's a mentored program, which means that obviously we'll expect that you will debate based on where in your journey you are. Some people are like Netflix architects who work on it. Some people are like, young who are journeying. Based on your skills, we will like give you an educational program of like what things you can get and learn, obviously from DeepLearning.AI, right? And then what part do you need to learn to start attacking? And then how can you start contributing on that specific problem once you have, gotten that educational attainment there? So obviously we want more open source contributors, but if it adds value to your resume, I think the best value is making an impact.
That's really nice. So, sir, the next question is like, what are the opportunities for an undergrad deep learning enthusiast, like for after the bachelor's, basically?
What are the positives or opportunities?
Opportunities, sir, like because.
Yeah, good question. So now let me tell you good news. No, it's the only good news coming out of the COVID world, which is that people realize they can actually work from home, or they can work from literally any country. So people in US are realizing, for example, that, hey, we actually never needed to hire everybody in US, and the jobs are actually becoming more remote. So people are getting used to that whole remote world. And that's actually good because the opportunities went from like being in India to being in India to being anywhere, right? Now, the problem is that, just to be a little frank, uh, I go through resumes, and when we go through resumes, people say, I have done a course on Coursera, and I have done this, and I have done that. And that shows passion, and that shows determination to learn this. And that's great. But uh, essentially, we miss out on like people showcasing something that they were so excited they built themselves, like a showcase project. Like, I don't have a way to measure somebody. I can't see that, is this person genuinely interested, or is this just there's a course and everybody does that, right? If you had done the course 5 years ago when many people did not have on their resumes, great. But today, everybody says they have done a Coursera course, right? So what I'm getting into is, if you can prove with a set of incredible projects, something which showed deep detail that you understood, you solved a program to solve captchas, right? It shows that you are interested. Actually, the code is not that big. It's on Keras examples, but it showed some intellectual curiosity of how you solved it. And then maybe you started attacking open source. That gets you an interest from the hiring manager, and then you can get there. But then comes the question of, what is the opportunity? AI is great. I should probably then maybe give a reality check also. A lot of people get interested, motivated with AI, but then you have to get into a little bit depth. And you know where the real depth is? Can you actually manipulate the data? I've seen like great Stanford students, excellent in their theoretical science part. They show their caliber, but if I actually give them a data manipulation exam to use in pandas and like play with the data, uh, it will take them a long time because they are not as familiar or don't use it on a day-to-day basis. So my request is, become amazing at data manipulation, at EDA, right? Because deep learning is cool, but you have to get to that data in the real world. We are not going to get there. You have to pick the right data. There's going to be data imbalance. There's going to be synthesizing of things you have to add in there. And that needs a lot of manipulation. I have usually found people who know manipulating data really well are usually the ones who can get a lot more out because their skills are just pure speed. I have found one website. It's dataquest.io. Usually, anybody who has gone through dataquest.io, and so it's like a website where you go in and they will have like one challenge for you on Python. But it's not like an interview coding lead code kind challenge. It's like a data manipulation sort of a challenge. So they will teach you without a video in text, and then you have to code it. And just that having to code it all the way yourself just puts it in your muscle memory. And I've seen people who have done amazing wonders. Like, person, English teacher, did not know what coding was. 1 month later gets invited to give a speech on how he learned coding at that level, and he said, I followed your examples. So I highly recommend dataquest.io.
Okay, yeah. So like I'll share the link in the description of about the dataquest.io. So the another question is that, like, while doing progressive resizing, how we will tell our model to use larger images for its training because the size it uses for training is fixed.
Fair question. So here's the story. So first part is, when you'll do this, you'll have to actually write 3 programs, or like one program at a time, like one program after another, right? So when you write your model, it's really the input layer which is really changing. You don't actually need. So imagine the input layer is 64, 128, 256. That's the input you set. The rest of the stuff can still be the same. 5x5 convolutional size, 7x7 convolutional size. That is not going to change as much. It's just the input that is changing. But what you do is you set a data pipeline and then train on that 64 into 64 resolution. Once it's trained, then you go towards 128 into 128. Then you go to 256 into 256, or you save the checkpoints after every train and go to the next and next. So I remember originally I used to be confused that, hey, my network is like so specific to this particular data set. Actually not. It's just the input word that you have to change, and things should work decently.
Yeah. So here's the last question, like, is there any way in machine learning we can reduce the need of such powerful resources? Like, I know parallel computing, quantum computing can solve these issues to some extent. Is there any other way available?
Yeah, so you might have heard this week the story of Timnit Gebru, who was writing a research paper at Google about uh, some of the amount of money people have to spend to train for some of these larger transformer models, and sadly, she had to part ways with Google and was fired on that particular paper. But the paper is actually already online and publicly available. But the point she was really raising is the fact that what the question you just said, the fact that uh, day by day, the progress we are seeing also is needing a lot more compute. And now what happens is only a few companies in the world, Microsoft, Google, Facebook, Apple, Pinterest have that kind of money that they can spend to go for those machines. And that's exactly why this lecture came into use, because you might be able to save 10x to 70x if you can just save money there. You might not need to go to that level. That's number one. Number two, good news is, yes, a lot of that processing needs power, but then for a real task in a real company, or even for academics, you don't need that power of a model, because somebody has already trained ImageNet, somebody has already trained GPT-2 and GPT-3. You just fine tune it in a couple of minutes. Number three is that you have Collab available, right? Or maybe you might go to 1 to 4 GPUs. You just need to pay the money for the number of hours you are training. So, for example, one of my teammates, his name is Rudy. He is writing a program to take images of planet Earth, but with no labels, and generate an embedding representation. So now we can search for examples of hurricanes and wildfires over the last 20 years, which were never reported before, right? And he does not, he has been doing this all on Collab, but he has a lot more data initially. So the way he operates is he runs the program on Collab, okay, till it's like finalized and I have everything running well. He knows that program is finalized. Then what he does is he takes that program and runs it on Google Cloud. And just for a matter of 1 to 2 hours, he rents out a machine with 4 GPUs. And we are basically paying for those 2 hours, right? Not that much money, right? For the power we get. But we end up training 100 to 200,000 images in those, 2 hours. And we have built, we realize we have done a lot of optimizations and some things we just cannot do, how much code we have to get into. But the point is, you pay for the minutes you use. So if you have to buy a machine, you might just be better off just renting it for a couple of hours and be happy with it. So works out.
So, like, I hope we have answered all the questions in the chat box. So, and I request everyone to please kindly fill up the feedback form that will be mailed to you by DeepLearning.AI team. And so here we are done with our session. So I'd like to thank Mr. Anirudh for such an informative session and taking time out of his busy schedule. Like, sir, we are actually honored to have you on Pioneer AI Bangalore. And moreover, I'd like to thank the DeepLearning.AI team and the Point Blank for their support. And last but not the least, like, I would like to thank all the participants for joining us today. Thank you so much. Thanks a lot. Stay home and stay safe. Yeah, goodbye.
Thanks, everyone.
Yeah,
Bye-bye.
bye.